Anyone on the in the audience, please, if you can, turn on your cameras, put yourself on mute. The intent of these sessions, and Jim will explain them in a few seconds, is to have a dialogue. Most of the times when you get involved in these sessions, they're, teacher presenting to audience. And, while that's fine and for the basics, this is intended to be a roll your sleeves up a little bit and dive into the details and show me what you just did there. So each of the sessions that we go through is intended to be a dialogue. Just raise your hand or come off mute, ask your questions along the way. We're structured so that this will be about a 15, 20-minute presentation with about a 40-minute Q&A. So you can ask anytime along the way. There's no formality here whatsoever. Having said that, Jim Bischoff and myself, we've been moderating the Passive Us Boot Camp for the last few weeks, and we'll be doing it again for at least the next 5 sessions that we have planned out. So Jim, you want to jump into that, please?
Yeah, thanks, Craig. Like Craig said, we've been doing this a couple of weeks. My name is Jim Bischoff. I work at Moss Architects, but mostly representing today Passive House, Western Pennsylvania. If you're on this call, I assume you figured out how to get here, but there's some more information there if you want to get future events, because each event has a new invite. Just to be clear, a couple of people have been asking how to get the future ones. After this one happens, in a couple of days, we'll send out the next one. We're covering all 5 of the principles for Passive House. Last week we did, or 2 weeks ago, sorry, we did continuous insulation. And
let me catch up to you. Sorry. You want to get into that first, or do you want me to call it done?
That's fine. Just a reminder, so in the last month, Passive House Western Pennsylvania became a chapter of NAPHN, which we're excited about, and you can become a member and join us. And to be clear, the way you do that is you join NAPHN. If you live in Western Pennsylvania, or basically the western half of Pennsylvania, you automatically become a member of Passive House Western Pennsylvania. No extra cost, no extra sign up, nothing like that. Just make sure you enter your address.
So benefits are discounted for training, discounts for our conference. We do a lot of really good online training with NAPHN. So, and you also have access to Passipedia, which is an incredible resource. If you're doing anything in the Passive House world, you need that resource. So joining us as a member will get you access to all that and more. And if you're interested, reach out to Jim or myself, and we'll be happy to talk to you.
Yeah, one of those benefits is going on right now, not as in like currently, but in the next 5 weeks or so, is the North American Passive House Network Conference. It's every Wednesday from, I believe, 1 to 4 or 1 to 5.
1 to 5.
It's a really great format because you don't have to spend 2 days on a webinar like some conferences are doing. Last week was the first week. This week, tomorrow is day 2, but the recording sessions, if you missed them, there's a little code at the bottom of the screen there. You can get a 15% discount just because. No membership, nothing required. You can just join. I highly recommend it. It's everyone. It's all the best people that talk about Passive House.
And what's interesting is for the conference, when we did our in-live conference, we were doing probably about 55 to 60 presentations. And now that we're online, we're down to about 25 to 30. So you're really seeing the most interesting and compelling presentations. Last week's conference, the presentations were just phenomenal.
I agree.
This is who we are. We'll be moderating the sessions, and we'll shut up very soon and introduce our expert speaker in about 1 second.
Yeah, just to reiterate what Craig's saying is we hope not to be talking too much. We hope people have questions. Each week our expert will speak for a little bit, but just for a short amount to sort of interest everybody and engage people with questions. Like I said, last week we talked about insulation. Now we're talking about thermal bridge-free connections and thermal bridge-free design. We will move on to the other ones in the future every 2 weeks. So windows in 2 weeks, air tightness in 4 weeks, and high efficiency heat recovery ventilation in 6 weeks. Those are all the dates. If you receive the invite, you get all the same dates. If you need more info, you can reach out to us, and I think our email will be up at the end again.
We'll email this deck out to everybody who registered, and then you'll see it in our social media, so you can attack it that way or just shoot us an email.
There you go. Yeah.
Thermal bridges. So we have Matt Bowers with us today. Matt Bowers is an expert in the passive house world. Matt is in the PHI discipline. If you saw our one-on-one 101 early, you'll notice that there's FIAS and there's PHI. Matt is mainly a practitioner in PHI. He's from Rochester, New York. He lives in a passive house, and he's been practicing passive house for a lot of years now. He is a passive house certifier. That requires an additional educational element of spending time in Germany with the standard writers, and he now certifies projects. Matt has an expertise in thermal bridge analysis and how to run those analysis and design a thermal bridge-free building. So with that, Matt, thank you very much for joining us today. Please grab the screen and begin.
All right, thanks a lot, Craig. Let's do this here. All right, so there is my beginning slide here. Again, my name is Matt Bowers. I'm the president of Rochester Passive House Consulting, and I'm also a member of Certifiers Cooperative, which is a group of 5 or 6 certifiers in the US, all throughout the US, and we work together and collaborate on certification projects. The reason I got into certification to begin with was because of a bad experience getting my house certified and the unresponsiveness of having to deal with overseas certifiers. So that was my motivating factor to becoming a certifier. I'm also a certified passive house designer and a tradesman. I worked for an insulation company for 10 years before I became a certifier and started my own business. So I've had my boots on the ground for quite some time now. And let's see. So for those of you who are certified designers or consultants, you may have heard this from your trainer, right? Just make your building thermal bridge free. It's so much easier. That's not really helpful. You know, that's that's one of the 5 main elements of passive house, and we're just going to say, just skip it if you can. And then later on in this slide, right, they'll talk about, well, to be thermal bridge free, your psi value has to be less than 0.006 BTUs per hour foot Fahrenheit. That's not an intuitive number or, you know, set of units for just about anybody. So usually you leave your designer or your consultant class with more questions about thermal bridges than answers. And so today I just wanted to talk in really, really generic terms on what is a thermal bridge, where can we find them, and how do we enter them into our energy model. So first, what is a thermal bridge? Well, it's really just a discontinuity of your thermal envelope. I know that that's kind of a cheesy answer, but really a thermal bridge is just anywhere in your model that is either not counted or counted twice. And we're going to account for that in different ways, and taking a look at the thermal effects that it has on your heating and or cooling demand. So there are 3 different kinds of thermal bridges. There's your repetitive thermal bridges, which are probably your most common. And a repetitive thermal bridge, the biggest example is going to be a stud in a wall. Okay, so this is a screenshot of your passive house planning package, which is a really, really phenomenal tool. It's your energy model. PHWPA is what it's also called. And this is just a screenshot of one of the assemblies in your R values tab or your U values tab if you're using the SI package. Okay, and we enter our repetitive thermal bridges right there, right? So it's just a percentage of the studs in your wall. Those are the most common repetitive thermal bridges. There are point thermal bridges, which are probably the thermal bridges that give people the most anxiety. And there are some side calculators within PHWPA or your passive house planning package to calculate those. And the most common point thermal bridges you're going to see in a house or a building are going to be cladding clips. But once in a while, you'll run into a larger issue, right? Where you've maybe got a steel I-beam that's going to penetrate your thermal barrier. And that might require a 3D thermal bridge calculation. And what I like to say about 3D thermal bridge calculations, which we talk about another day, they're really, really intensive. A single thermal bridge model could probably run between $3,000 and $5,000, and it's going to take somebody who knows what they're doing almost a week to complete.
A 3D model.
Yeah, a 3D model. And what I would recommend is that you spend that $3,000 to $5,000 improving the design, right, and make it so that the I-beam isn't necessarily penetrating if you can avoid it. So moving on to what I would really like to talk about today are your assembly junction thermal bridges or your linear thermal bridges. And those get entered in the areas tab of your passive house planning package, way down at the bottom where there are some entries for your thermal bridge inputs. And you're going to enter your calculation from either Therm, which is a two-dimensional thermal bridge calculation tool, or Flixo, which is a much higher end, more intuitive thermal bridge calculating tool as well. So you're just going to enter your psi value, which is a BTU hour foot Fahrenheit, and you're going to enter it right there. So let's talk about some typical linear thermal bridges. Okay, it's going to be any corner in your building, right? So this detail is a slab to a basement wall. Okay, this detail is going to be a plan view corner detail, right? So this is a double stud wall with sheathing on the exterior side of the interior wall. This is a detail from my personal house. Okay, so we've counted this corner twice, the corner piece twice, and I'm going to talk about that in a minute. Your eave detail, right? All of these details can be further analyzed as thermal bridges, and we want to make sure that they're not going to be condensation points as well. Okay, if you've got a wall section, you can see right here, you've got a band joist where we've got some extra framing happening between the first and second floor, and then certainly your rim joist detail where you've got concrete and insulation somehow connecting to a flooring system and then an above grade wall. So this is certainly a thermal bridge that's worth taking a closer look at. And then maybe my pet peeve or a soapbox is going to be window installation. I'm a big one for window installation details because they can have maybe the biggest impact of any linear thermal bridge in your building. Okay, and I'm going to talk about that as we move on here. So just general information, what is a thermal bridge and what does the calculation kind of look like? So we're going to take this detail, right? So this is your two-dimensional thermal bridge model, and then we're going to subtract from it what we've already included in your thermal bridge model, which is an above grade wall and another above grade wall. And how they come together is going to give you your psi value. Okay, so we're going to subtract the true heat loss of the corner from what we've already accounted for in the energy model, which is why you're always going to be measuring your building with outside dimensions, because it's consistent and it's going to yield better, more conservative results without having to analyze any thermal bridges. So this is a screenshot of a Flixo model of a thermal bridge calculation. So this is kind of what the output of the calculation is. And what we've got going on is we've got our formula here at the bottom, okay, with lots of Greek letters and letters with sub numbers. And what do all of these mean? So our psi value is going to equal our heat loss number, right? The actual heat loss of the model, which is 13.0, divided by our temperature difference, right? And because we're in SI units, it's going to be 20 degrees Celsius minus a negative 10 degrees Celsius or Kelvin, and it's going to give you a 30 degree Celsius / Kelvin delta T. Okay. So that's one part of the formula. Now what we need to do is subtract from it what we've already accounted for in our energy model. So our U value between, it's tough to see, but this is F and A. Between F and A, our U value is going to be 0.102. And these numbers might not be intuitive to you, but the process is going to be the same whether we're working in SI or IP units. Okay. And then, so we're going to take the U value and we're going to multiply it by the length in the energy model. Okay. And we're going to do the same thing for the other wall. So between C and H, our U value, and this U value should be pretty close to what you have for a U value in your energy model, whether that's PHWPA or WPA passive, times the length. And then that all comes together to be negative 0.054. And if we do a quick unit conversion, that gives us a negative 0.031 BTU per hour foot Fahrenheit. So this detail is considered thermal bridge free. Okay. And what we're going to do is we're going to take this number and we're going to input it into our PHWPA. Okay. So we've got above grade wall corner. We've got 4 corners that are 21.28 feet tall. And then the psi value that we just calculated is negative 0.031. And that's how you enter a thermal bridge once you've actually done the calculation. Okay. Now I do have a set of thermal bridge calculations all ready to go that I just wanted to kind of go over with you. This is Flixo, and it's much more intuitive than Therm. And what's really nice about it is it does the reporting for you. So you don't need a separate calculator to do it. But what we've got is our thermal bridge calculation. This is the one that I just showed you, right? So negative 0.031. Now, if we look at it from the other perspective, right? The blue line, and I'm zooming all over the place here. The blue line is your exterior boundary condition. Okay, so if we were to take a look at this corner as an inside corner, right? We've got our exterior condition here, and maybe we've got a bump out or something going on. If we look at that detail, let me zoom to page width here. Okay, so now our lengths have gotten shorter. We might have a little bit more framing in the corner, and this is going to yield a positive thermal bridge. And this number is 0.016 BTU per hour foot Fahrenheit. This is a positive thermal bridge. And this needs to be accounted for in your energy model. This calculation is a really, really quick calculation. And let me just I'll show it to you on the next one. So this needs to be entered in the same method as the outside corner does. I like to think of thermal bridge calculations as more of a correction factor than really anything else. So here are 2 different scenarios we've got. This is a band joist connection, right? A 2-story band joist connection. Our first floor double wall and our second floor double wall. And then there's always the question, right? Which wall is load bearing, and does it really matter? So in this case, the exterior wall is load bearing because you can see that the floor joists between floors are sitting right on the wall, and they're penetrating this thermal thermal barrier. On this detail, the interior wall is load bearing. And you can see that it's just kind of sitting on the interior wall. And then in this case, we actually had to create a fire block between the first and second floor. So we've got the second floor subfloor going across, okay? And if we take a look at these two models, we've got nearly a thermal bridge. So the first detail is over here, and we've got a thermal bridge of 0.012. So this is a positive thermal bridge. And on this detail, it's nearly thermal bridge free and maybe addressing a higher R value on the band joist right here would make this a thermal bridge free calculation. So there certainly is a difference when it comes to inside wall to outside wall load bearing when it comes to double wall construction. And really, so the meat of what I wanted to talk about is going to be the window installation, okay? So we're going to look at three different situations: an inside, a middle, and an outside mounted window. Same exact detail, and this is a close-up of the inside mount detail, okay? The window is mounted right on the inside. We've got a little bit of a slope coming through over here to shed water away. This is your thermal image diagram that kind of shows isotherms going. And then this is actually our calculation over here. And if we look at this, we've got a thermal bridge number of 0.024, which is pretty close to what the manual says is a default value. So that's not a great number, but it's not a terrible number either. So let's skip to the outside. And all we're going to do is move the window to the outside. It makes this piece of trim shorter on the outside, but now we've got more trim on the inside. And again, the isotherms are moving pretty consistently, just in the opposite direction. And if we look at our psi value calculation, it's positive 0.23. So they're nearly identical numbers, whether it's to the inside or to the outside. But what happens if we just move it to the middle? Okay, so now we're putting the window in the middle, and as you can see, the isotherms don't have to make such a jagged turn one way or the other. The isotherms can be a little bit more straight, and the window has, you know, a similar trim detail. They're just smaller on either side. And then we look at this number. Okay, now our thermal bridge installation for the window is 0.010, which is nearly thermal bridge free. Okay, and all we did was move the window to the middle. And how much could this possibly matter, right? So there's about 350 linear feet for a single family house of window installation thermal bridge. Okay, so if we input those into our PHWPA, okay, we're starting with a heating demand number of 4.46, and our magic number for passive house is 4.75, right? So we want this to be under 4.75 when it's all said and done. So we enter our 0.023 value, and we're still meeting passive house level heating demand, right? But if we change that to 0.01, which is putting the window in the middle of the wall, over 350 linear feet is going to significantly reduce our heating demand, right? So 4.18 now from 4.46. That's a significant difference, and all you're doing is moving the window to the middle. That's a 6% difference, and you're probably looking at adding another 2 inches of insulation to the outside of the house to make up for that. Okay, that was a real quick overview for everybody, and I would be happy to answer any questions. Let me just open this back up here.
Hey, Matt, why don't you keep the screen?
Yeah.
we might be dipping back into Flixo here and answering some technical questions. We got some technical people in the presentation.
Let me pull it up here. So let's see. So yeah, if you have any questions, feel free to unmute yourself, and I would be, if I don't know the answer, I'll make something up, but I'll find the real answer for you, I promise.
So I guess I'll get it kick started. Please come in with any questions. How about the location of the windows? Are the location of the windows climate zone specific? Are you finding that there's a correlation to climate zone, or are you just pretty much generally locating this in the center of that wall first?
So in general, I always want to put the window in the middle of the R value of the wall. And the reason I say it like that is wall assemblies can vary, right? You can have polyiso on the outside of a 2x6 wall, and a majority of the center of the R value isn't necessarily going to be the center of the wall. With a double wall, it works out that it's smack dab in the middle, but it's important, and that's going to affect your install psi value just based on being in the middle of the R value of the wall. With respect to climate zone, the impact, the psi value is going to be the same regardless of climate zone, but the impact it's going to have on the energy model is going to be more climate zone specific, if that answers your question.
It does. Now, in your model here, you have insulation in both service cavities of those stud walls, correct?
Yes. So the overall makeup of the wall assembly, if I was to describe it from the inside to the outside, we've got drywall, 2x4, 16-inch on center. Okay, and this was actually our load-bearing wall, and I'll describe it here in a second how that's the case. On the exterior side of the interior wall, we have Intello. And then we've got about 12 inches from the Intello to the OSB on the outside. And so this 8-inch cavity was dry blown, dense packed cellulose. And then this is a 2x4, 16-inch on center cladding wall with OSB on the outside. And then we had Tyvek on the very outside. What we did was we actually, at the band joist, when you connect the two walls, and let's see if I can zoom in a little bit better here. When you connect the two walls at the band joist with the second floor subfloor, you can transfer the shear strength from your shear wall to your load-bearing wall. So it was a fairly complicated wall assembly, but we needed sheathing on the outside because the homeowner really wanted vinyl siding, and you need a backer for vinyl siding. So that's what we came up with.
I'm taking a breath, giving our audience plenty of time to come in with all these great questions.
Yeah.
Greg, I have a question.
Gerard's got one.
All right, Gerard.
So are there any situations where you have different orientations where you would put the window location within the wall at different depths? Like
Yes.
if you're trying to take advantage of like free heating or something like that?
So yeah, and that's a really good use of design pH. You can build the building in SketchUp and then change the recess of the windows to take advantage of the shading elements of your buck, and then you can weigh that against what the thermal bridge value is going to be. So there is a way to do that. Most commonly what I see is doors are going to be installed all the way to the inside so that you can open the door 180 degrees. And then there usually aren't too many doors in a house or a building. So you can take that minor hit of having a thermal bridge for the convenience of being able to open the door all the way. So Sonia was asking to walk you through a thermal bridge modeling process in Flixo. All right, so let me do a band joist because
I
that
want to make sure too that we get all the questions, because that could take a while, right? It's complex. It's kind of complex. Usually we had Flixo training in Pittsburgh a couple of years ago, and it was a 2 or 3 day course.
So this will take 10 seconds.
That's cool. I'm just making sure like people understand.
Go at 20.
I'll give
Learn to use
20.
the program is going to take.
So we've got our model already created. Each one of these polygons has been given a conductivity. Okay, where it's hatched is where we have repeating thermal bridges. Okay, so this is a 2x4, 16-inch on center with cellulose in the cavity, right? So the hatched polygons are accounting for repeating thermal bridges. Now all we need to do is we're going to select psi value. We want to do a psi value calculation. We're going to select the beginning point and the end point of the model. So we're going to start at the top, and then we're going to scroll down to the bottom, click there, and then it needs a reference point. It wants to know what are we comparing to what. So somewhere in the middle here is going to be our reference point, and I'll click there, and then Flixo does this calculation for us. It gives me it senses where the U value is for the top and the bottom wall, right? It gives me my total unit heat loss, right, which is a phi value. This is the Greek letter phi. And then it does my dimensioning for me. And then it spits out this cool little equation, and there's our psi value.
Hey, Matt, you said you really like Flixo because it provides a report that's easily submitted to PHI for certification around these bridgings. Can you talk about that?
Yeah, so the first thing we do is we can import models into our drawing page, right? So this is kind of our paper space where we create the model and we give everything an R value, okay? Right, this is a 2x4 16-inch on center with our 3.8 in the cavity. So we build all of this, we give it boundary conditions, which are already in the program, right? So the boundary conditions are going to be minus 10 degrees outside, and then 20 degrees Celsius inside, and we can change the units fairly easily. We build it here, and then we hit this play button, and it'll go through all of these different iterations, right? So if I just did this, and we hit play, it's going to run, and this is very similar to what Therm does, but Therm kind of stops here. Stops here, okay? And it'll spit out maybe a U value or your heat loss value, but it won't put it into an equation for you. So you need to be able to have a secondary calculator handy. So that's where Flixo has the reporting feature where it'll just take this model, and we can take this model and we can add isotherms, right? Which are the lines of where the temperature gradient within the wall is. So we can add isotherms. We can make it a temperature field. Oh, I'm sorry, streamlines. Temperature field, which is the pretty little rainbow color, right? We can add a heat flux field, which is another feature where it's focusing the heat loss points. So there's all kinds of different reporting view types and things like that we're able to do with Flixo. And we can add other objects to the same report so we can compare models right next to each other. And once you have your reports all set up, it's really, really quick.
Sonia, if you have any other questions on Flixo, please come off mute or throw them in the chat and we can continue. We have lots more time. The intent of the presentation was really to spend some time in here. If anyone wants to go back or forth to any of the details that Matt has graciously set up for us, just ask.
Hey, Matt, we talked a little bit about thermal and energy impacts, but what about condensation, identifying condensation risk? Can you talk a little bit about how that works in Flixo?
Sure. So what we've got is there is another calculation called FRSI, Okay, and which that's more of a climate specific number, but it kind of tells you what your minimum allowable temperature is based on your climate zone to ensure you're going to be condensation free. So if we took a look at, we'll do the outside window model, and the only thing different between an FRSI calculation and a normal thermal bridge calculation to get your psi value is your exterior boundary condition, or I'm sorry, your interior boundary condition. So what I'm going to do is we will edit, select. So I'm selecting all of my boundary conditions and I'm going to delete them. All right, so what we're going to do is we're going to add some more boundary conditions now. So we're going to start with our line of symmetry where our model cuts off and continues. So we're going to click here, and then the boundary conditions are distributed throughout the model in a counterclockwise fashion. So now we're going to come around, and everything right now, there are no boundary conditions in the model. So our next boundary condition point is going to be up here where it's an interior boundary condition. But given that we're going to do an FRSI calculation, we need, and I don't know if I have. All right, so you caught me here. I'm going to have to create a new one.
I didn't mean to put you on the spot.
No, that's all right. So, so the normal FRSI boundary condition surface film value is 0.25. So I just have to create that. And now what we're going to do is take this new boundary condition and we're going to add it on the inside. And this boundary condition is going to go all the way around until we get to the bottom of the model. And this is, again, where the model cuts off. So we're going to draw our line of symmetry. And then our exterior boundary condition is going to be, we have ventilated cladding, right? It's vinyl siding. So we're going to use exterior ventilated boundary condition there. And that's going to take us all the way up to our other point. And we actually transition, like right here, to exterior normal, so where it's not ventilated cladding. All right, so that takes us to there, and now we just hit play. And then it's gonna pop us over to our window. Our window report when it's done doing its calculation. Okay, so here we are. And now what we're gonna do is a min-max temperature. And we're gonna take this and we're just gonna go select somewhere on the glazing panel here. And maybe down to the wall. So now we have our FRSI value, right, 0.762. And this detail would have condensation potential in a Arctic setting. I think Arctic FRSI calculations have to be 0.8 or above. But everywhere else in the world, this is going to be a condensation-free design. And this value is available on Pacipedia and a variety of other, this value's limits are available, and they're all climate zone specific on Pacipedia. Does that answer your question?
Yeah, that's a good demo.
So Matt, when you're looking at a detail and you know you're concerned about it from energy standpoint, what drives you to decide you need to check the hygiene requirement or the condensation for a certain detail? Or
usually I'll do it for a window, and if I have to do the detail anyway,
yep.
It's really not very cumbersome to add this extra model. It'll, I mean, I just did it in about, I don't know, a minute.
Yeah. So it's
really not that big of a deal to have to do this extra calculation.
And it's totally possible that you could model a detail for thermal bridge and get its psi value, or whatever it is you're looking for based on geometry, and account for it in the energy model, but that condensation potential may dictate that you have to change the detail, even though your project is meeting the energy goals. Is that correct?
Yeah, so if we were to look at this model, right, an outside corner, I think everyone would agree that, yeah, this is probably a thermal bridge free design, right? And the psi value is negative. But what would happen if we just did this, right? And we're going to put a big solid wooden post right smack in this corner. I think everyone would agree that that's probably not thermal bridge free, right? But if we ran this calculation, okay, and took a look at the report here, so we've got our U value being accounted for here and here, right? And this is our psi value calculation, and it's still negative, right? So just because you have a negative psi value or a really low psi value doesn't necessarily mean that it's a good thermal bridge detail. Good
Hey,
question.
Jim, we got a couple questions in the chat. Ian, did you want to come offline to ask your question? Or come off mute, I mean, sorry. I can ask it. Ian wants to know, are there a lot of calculations that need to be done outside the modeling software that require a building science expert knowledge, or does the software take care of most of this on its own?
Once you learn how to do it, it's very intuitive, and it can be very, very quick. Don't let programs like Therm scare you. And once you know how to do it, and have gone through the process once, you'll know what to look for in future details on how to make your designs thermal bridge free. I don't know if that necessarily answers your question, but I know that architects sitting out here watching this, there's like, now I've got to learn another software, and I've got to have another subscription to something, and all of it. Well, I'm no, not doing
Just
this.
make it thermal bridge free, like you said.
Just make it thermal bridge free, right? Yeah, exactly.
Go back to slide 1. In terms of doing this, though, there's a lot of people that have gone through Passivage training, and they're very interested and they want to learn how to do this. And maybe they've gone through a Flixo training, so now they know the basics. But doing these can get you into trouble if you don't know what you're doing. Does PHI, and I'm limiting my question to PHI because your background is with PHI and not Theus, does PHI through its certifiers offer peer review in this instance?
Yeah, and as a certifier, what I'll say is, if we run into a situation, usually we run into a situation where the designer has gone through the training, has maybe taken a Flixo course, but they're still green, right? They don't have the experience to really know what they're doing. They're still kind of learning, right? Another one of the certifiers in our cooperative will take them under their wing as a coach, and we can coach you through these details. And then we can still maintain the 4 eyes rule that PHI likes to have on their certifications by having another certifier do the actual certification.
And also, this is why Passive House Western Pennsylvania exists, to become a peer review maybe before. So coming in with those really simple questions and, hey, I did this, can you check it, and have an eco network that we can rely upon. But then once you get into the guts of a project, you do also have that additional belts and suspenders of the certifiers that will do those peer reviews. They won't do the details, but they'll do the peer reviews and give you guidance and coaching.
Right.
Excellent. Thanks, Matt. Paul Heron has a question, and he does not have availability to a mic, so I'll read his for you. On the window placement in the wall assembly, if you have an assembly with 2-inch continuous polyiso, then dense pack in the 2x6 cavity, the placement of the window in the assembly would be in the center of the R value, correct? Which in this situation might be slightly more to the exterior due to the continuous polyiso, with a slightly higher R value in the dense pack, correct?
Yes, absolutely. And the other thing to consider when you have exterior insulation like that is another thing that can impact your your window install psi value, and I'm going to open up the outside report here, is if we have, I'll get it there. If we have continuous insulation on the outside of this, we also have the ability to bury some of the frame in insulation, and that can further help lower your psi value. Okay, so when you have, if this is a 2x6 wall and we've got polyiso on the outside, we can run that polyiso up and bury some of the frame of the window. A lot of these passive house windows have really, really thick frames, and they're designed to be buried with exterior insulation for that purpose.
Mm-hmm. Sometimes you can order, if you have like aluminum clad window, you can order the aluminum cladding to be held short so the insulation can go back up to the window. The other point though too about, I would say, right, deciding exactly where to put the window. Hey, Nick's got one, he's holding it up.
So there's this can be buried with insulation to further improve your psi value.
Yeah, I think a lot of people refer to that as over insulating, which I think is a funny term.
Yes.
Because it's almost like, how do you over insulate? But the other thing I would say with window placement, right, is you could get this down to the like specific spot. You absolutely love it, but you still have to build it.
Yeah.
It has to be constructible, and it has to be durable, and it has to work with water and air too, right? So you go through iterations, you find a good one, and someone says, well, how the am I supposed to build that? And now you got this weird condition, and I'm not familiar with doing a window that way. So every project, you can have the same wall, similar building, different people building it, might get a different detail.
Yep, absolutely. That's a very, very good point.
Yeah,
buildability of all of these details is critical.
Jim, but to your point though, I mean, what we're seeing in practice is a lot of people are figuring that standardization out, and then they're able to duplicate that and use it on projects moving forward.
Yeah, you get a little more confident in every project. You get a little, I've seen it done. Now I can tell the contractor a little bit about the detail, the intended detail, and it gets better every time for sure.
Yeah, no doubt. I'm taking a breath. Any more questions? I have a few more that I'd like to ask, but come on in, ask your question, please. So Matt, how does shading come into play when you're talking about window placement? I mean, you're doing it from a thermal bridge perspective, but shading has value as well. And, how do you balance the value of shading from heat gain or controlling heat, hot spots versus, getting your thermal bridges perfect?
So you're not going to be able to do much when it comes to shading on the north, east, and west side of a building, right? You can have a 35-foot overhang, but if there's no horizon shading on the west, you're still going to get solar gain for some time during the day. So window placement on those three sides tends to be a better value if you can optimize the window installation detail. If we're talking on the south side, I think it varies on how thick the wall is. And there are other things to consider on top of the shading, right? If you have a 2-foot thick wall and you're going to put the window all the way to the inside, as you're looking out that window, if the window's not big enough, you could get this tunnel vision kind of look, right? If you put the window all the way to the outside, depending on where your air barrier is, that detail can be very, very tricky. So the shading element is something to certainly keep an eye on, and it's going to vary based on how thick the wall is to begin with. But typically, it's going to be easiest in the middle anyway. Maybe a hair to the outside to get your moisture resistance, watertight assembly completed there. But usually you're somewhere between the smack dab middle of the wall and closer to the outside.
Thank you. So we have time for a few more questions. Rebecca, I told you I'd call you out towards the end. I waited all the way to the end for you.
Ooh, pressure.
There she is.
And on camera.
I'm trying to finish something for a deadline, so I'm listening.
Any questions for Matt?
No, this is great. It's been a while since I've been in Flixo myself, so good to see it.
Does anyone else have any other questions? We got a couple more minutes.
Well, if no one's got any other questions, let me touch real quick. This is a PHWPA that I have hidden a lot of tabs. So this is all that I'm showing right now. I don't know if everybody knows this, and they really don't talk about this in any of the trainings, but the IP version of PHWPA is just a skin for the SI version, okay? And what you do is you unprotect, right? You come over to review and you unprotect the workbook, and that allows you to see all of the hidden tabs, right? There are, all of these tabs are hidden. I'm sure you can hear my wife just got home from work. So all of these tabs are hidden, and every tab has an SI tab associated with it. So that can certainly help you be able to transfer information from units from one to the other. Okay, so you have an R values tab and a U values tab, and they're linked, and they do the unit conversions for you. And this is the section. So I'm in the areas. I'm kind of moving fast here. This is the areas tab of the PHWPA. Just scrolling down, scrolling down, scrolling. There's your thermal bridge inputs right there. Okay, so this is where you would input all of that information from your psi values. But when you have the IP version of PHWPA, you actually have both. That will help people in the future. I didn't know that until I became a certifier.
It's in the other units, but isn't a lot of it also in German?
Well, so then we can start going to like this area here. Oh, I've got to unprotect the sheet. So if we just keep scrolling over, right, and we start unhiding tabs.
Yeah.
There it is. So yeah, so this is now all in German, and this is where all the calculations are actually done, is off to the side.
That's where your brain explodes.
Yeah, that's where you got to have Google Translate up to figure out what's going on. But if you're trying to, I'm sorry.
That includes the climate sheet. Also has the SI page.
I hid the climate sheet.
Yeah, that's fine, because I had to pull in climate data and I converted it all.
Yeah,
I pulled in climate data from Pacipedia, and I wish I'd realized that there was I should have known that. I just didn't.
So you have climate and climate SI.
So I could have just dumped the climate sheet in there and then not had to convert everything.
Yes.
Yep.
Gary, we'll be learning those little tricks for the next 10 years.
Oh yeah.
There's also a super useful conversion tab, right? The very end.
There is, yeah. I've used that a few times. Yeah.
Very helpful conversion.
But when you have a whole table full of climate data to go through, it's.
So when you're designing in Design PH, everything is SI. So I usually like to start by building my U values, building my R values in PHWPA, and then opening my U values tab and just copying this information over, right? Watt per meter Kelvin values and millimeters right into Design PH. That's the quickest way to get good values in your Design PH model.
Alrighty, well, we are right up against it. If there's any other questions, we've got time for one more. All right, then I will grab the screen here real quick. We'd like to show you. So we've been through a Passivhaus 101. That was our first week. We've been through climate-specific insulation levels. That was 2 weeks ago. Today, thank you to Matt, we had an awesome presentation on thermal bridge-free connection. Say that quick 3 times. And then in July 14th, we have a presentation for high-performance windows and doors. Jim and I are still curating this event. We'll have something to you guys probably right after the holiday. But if you can mark your calendars, those are the next 3 dates. We're also taking in suggestions for ideas. So after we come out of the 101 and the 5 parameters, the 5 elements of a passive house, then we're going to start doing a little bit of a deeper dive into things that Matt was doing today around PHWPA, subcomponent models, QA, QC. We have a great resources in Western PA for QA, QC. We want to start diving into those. If anyone has a subject matter that they're on their project or they see or they'd really like us to expedite, send Jim or myself an email. We're happy to do it. We'll prioritize that and do that right after we finish air tightness and the high efficiency HRVs, ERVs, and HRVs. And we'll hit that probably right after those sessions. So with that, I want to thank everybody for attending today. I really want to reach out and thank Matt. Matt, amazing presentation. You're a great resource. Thank you for joining us today.
You're welcome, guys. Go Bills.
Whoa.
Oh, you're killing me.
Cut that off from the recording.
We're not limited to Pittsburgh here, Matt. But we do have a reach. We can go across the state and into Ohio, but not quite the Bills territory.
Go Bills.
All right. Thank you very much, everyone. Have a great evening, and we'll see you next time.